All right, so we're talking about polynomials today, and we're going to talk about uh, x-intercept. Let's do the next intercept of a polynomial to get started here this morning. So if we graph, and I have one of these already up here, y equals 2x to the third plus x squared minus 14x minus 21. When we graph that, the graph looks like that. I can zoom out so we can see it's the kind of curve it's got. But when we zoom into there, we see that it crosses the x at 3, right? So if I get right out there, it is 3, 0. So it crosses the x at 3. So that tells us something. That tells us something about a factor. That means that x minus 3 is a factor of that polynomial. So we can factor that out. You can do polynomial long division. Not that anyone wants to do polynomial long division, but we can do that. All right, so we look at x minus 3, and how many times we look at the first terms here. How many times will x go into 2x to the third? It goes in there 2x squared number of times. All right, so we're going to take that 2x squared times x minus 3 underneath. So 2x squared times x is 2x to the third. Minus 3 is minus 6x squared. Subtract, right? So that goes away. We've got negative 5x squared. How many times will x go into negative 5x squared? We'll bring down the negative 14x, right? So that'll go into there negative 5x times. So negative 5x times this is negative 5. Oh, let's see. Yeah, negative 5x, because we're going to subtract minus 15x. So when we subtract a negative from a negative, it zeroes out. And we subtract this, we end up with just an x, right? X minus 21. Is that right? Negative 14x. Trying to make sure I haven't messed anything up going down here. 2x squared plus x. Oh, I was subtracting. That's what I messed up. I messed up something already. Subtracting. So I subtracted this incorrect. When I subtracted a 6, that means I'm adding 6. That's going to be a plus 7. So this is going to go in here plus 7 amount of times. So that's 7x squared. And this is going to be minus 21x. Whew, it's early in the morning to be doing this kind of math, isn't it? It's all right. We'll get awake here. So this is going to be, when you subtract 21 from the 14, it's a positive 7. So that's going to go in there 7 amount of times, right? 7x minus 21, 0. Yeah, we should have a remainder of 0. So when we factor out an x minus 3, we know we could write this now, because when you factor it out, it leaves 2x squared plus 7x plus 7. Long division. You got to be careful subtracting here. Subtract a negative, add. That's what I made a mistake on. Figured that out. We can do long division. So this is one that works out real nicely, and that's the new factor. But what happens if it doesn't work out with a nice? Well, that's okay too. Sometimes it doesn't. Let's look at one that does not come out so nicely. Let's take 2x to the third minus 3x squared minus 2x plus 6. And we're going to factor out of that x plus 1. Okay, so how many times will x go into 2x to the third? 2x squared. This starts out like our last one did up there, right? 2x to the third. So when I multiply that, I've got 2x to the third and then plus 2x squared. So I'm going to subtract that. That goes away. Negative 3 minus 2 more. I've got negative 5x squared. Right? How many times will x go into 5x squared? I'm going to bring this 2x down. Well, that's going to go in there negative 5x times. So we got negative 5x times. So negative 5x squared, negative 5x. Right? Subtract that. This goes away. Negative 2 minus a negative 5 is adding to 5. So this is going to be a positive 3x plus 6. How many times will x go into 3x? It'll go in there 3 times. So 3x plus 3. And we have a remainder of 3. So that means we could write f of x this way. Instead, start out with this. But we know x plus 1, if we factor it out, leaves 2x squared minus 5x plus 3 with a remainder of 3. We can rewrite that, factoring out x plus 1, to be this right here. And we're like, oh my gosh, I hated long division with numbers. Now we're doing it with variables. All right, well, let me show you something else that you might like. We're going to look at synthetic division. If you haven't seen this before, let's say that I want to take x minus 3, and I'm going to divide it into 2x to the third minus 3x squared minus 5x minus 12. And we're like, whew, okay, well, let's say we want to do that. Here is how synthetic division works. If x minus 3 is one of our factors, x minus 3 equals 0. So that means x equals 3. So that means 3 would be one of the x-intercepts, right? That would be one of the zeros. We're going to take that 3, and we're going to divide that into, and I'm just going to pull the coefficients. 2, negative 3, negative 5, negative 12. That's all I'm doing, taking the coefficients. I'm going to leave some space in there because we're going to need some space to work. So I'm going to bring this 2 straight down. The 2 comes straight down. Now I'm going to multiply. 3 times 2 is 6. And I'm going to add these together. Negative 3 plus 6 is 3. Multiply. 3 times 3 is 9. Add those together. That's a positive 4. 3 times 4 is 12. Negative 12 plus 12 is 0. This is what happens with synthetic division. This is the remainder. So there's no remainder. This is the constant. This is the x term. This is the x squared term. When I divide x minus 3 into this, this is what it leaves. So I can rewrite it as x minus 3 times this. Synthetic division. We could do the long division, but we would end up with the same thing. We would have 2x squared plus 3x plus 4 with 0 remainder. Synthetic division is your friend. That's all it took to do that. So let's, and if you had a remainder, it would, if we had a plus 4, whatever remainder, we can write it on the end like that. Sometimes they would put a remainder of, like if this had a remainder of 4, we would say the remainder is 4 x minus 3, 4 over x minus 3, because that's what we were dividing by, the x minus 3, right? 4 over x minus 3. But with the synthetic division, it's going to tell us on this one, there is no remainder at all. So the question is, if we're going to do that and we're going to figure out what are the zeros, because 3 is one of the zeros there. Is there a better way to do that than just throwing numbers out here and doing synthetic division? Yes, we have what we call the rational zeros theorem. So let me give you an example of how this rational zeros theorem works. So if I have, we're going to do P of X. This is an example, actually, is from your textbook. 2x to the fourth plus x to the third minus 19x squared minus 9x plus 9. Oh, let me just say something about synthetic division real quick. If we had 2x to the third minus 5x plus 1, and we were dividing it by x minus 2, when we did synthetic division, we would take that 2, because x minus 2, so that means 2 would be the 0. And we would have to write the numbers, the coefficients. We would put 2, 0, negative 5, and 1. And the reason we do that is because we're missing the x squared term. The coefficient for x squared is 0. But with synthetic division, you have to start with the highest exponent and write the coefficient for every term after that. So if you see an x squared missing from your polynomial, you have to write the 0 coefficient for it. It has to be in there, or it's going to mess up your synthetic division. So don't forget that if you're using synthetic division. Every term has to have the coefficient, even if it's a 0. So, all right, let me go back to this. Rational zeros theorem. So it says if you have a polynomial that is higher than just linear, it has an exponent of greater than 1, and this is not a 0, then we can figure out all the possible zeros for this. And the way we do that is we look at the constant first and figure what are all the factors of 9. Well, the factors of 9 are 1, negative 1, 3, negative 3, 9, and negative 9. I'm sorry, negative 9. Because we can multiply 1 times 9, negative 1 times negative 9, or 3 times negative 3. That's all the factors that can make up a 9. And we can simplify that to say plus or minus 1, plus or minus 3, plus or minus 9. And that's the way the textbook is going to present a lot of times. Plus or minus, we'll just combine them. That's all the possible factors for that, for the constant. Then we look at the first term. What are all the possible coefficients there? Well, that's just plus or minus 1 times plus or minus 2. That's the only factors there are. So to figure out what are the possible zeros for this here, we take, and they label this the P and this the Q. We're minding our P's and Q's here. They call this the P, and that's the integer factor of the constant, and Q is the first coefficient. And if we take P divided by Q, that will tell us all the possible zeros of this, all the possible zeros. So that means 1 divided by 1, which is, 1 divided by 1 plus or minus. We can have, we can go with the 2's in, so plus or minus 1 divided by 2. Then we have plus or minus 3 divided by 1 and 3 divided by 2. All these are plus or minus. And then plus or minus 9 divided by 1 and plus or minus 9 divided by 2. All right, so we can simplify that. This is just 1 plus or minus 1 plus or minus 1/2 plus or minus 3 plus or minus 3/2 plus or minus 9 plus or minus 9/2. All right, so from all the possible zeros in the world, we've narrowed it down to basically a dozen. 1, 1/2, 3, 3/2, 9, 9/2, or the negatives of any of those. And so doing that, and our textbooks actually goes through there and starts checking several of them. Our textbook starts going through with synthetic division to make it quick. And they've checked 1, -1, 1/2, -1/2, and 3. And what you find is if it has a remainder, then that is not a 0. Like when they checked 1 through synthetic division, it has a remainder of -16. So that is not one of the zeros of this equation. -1, however, has a 0 remainder. So it is a 0. As far as 1/2 also has a remainder 0. So it is also a 0 of this equation. -1/2, however, is not. +3 is, and they go on and they put etc. here. They don't show us all of them, but they also find out that -3 is. So this actually ends up with 4 different roots. Now, the thing we know, since this is a polynomial of degree 4, 4 is the maximum number of roots it has. Once you find 4, you can stop because there are not any more than that. So it turns out these -3, -1, 1/2, and +3 are the 4 zeros for this, but there will not be more than 4 because it can have less than 4. It just cannot have more than 4. So you're like, wow, that's a lot. Is there any way we can do to narrow that down where I don't have to do a dozen of them? Because if it turns out the last one you check is your 4th root, you'd have to do all 12 of them. Yes, there actually is. We have an upper and lower bound test for real zeros. So let's look at that. Okay, so examples for find the real zeros. You may have a problem, and they present some problems like this where they'll say, prove that all the real zeros, let me write this function down, 10x to the 5th minus 3x squared plus x minus 6. It's going to say prove that all the real zeros are between 0 and 1. That there's no zeros smaller than 0 and there's no zeros larger than 1. Okay, well, there's a way we can do this with synthetic division. So let's start with the 1. We want to prove that there's not any larger than 1. So if we take 1 and do synthetic division, and again, we take the coefficients, 10, x to the 4th and x to the 3rd are both missing. So we got to put a 0 because they both have a coefficient of 0. Then -3, 1, and -6. All right, so doing the synthetic division, we take the 10 and drop it straight down. Then we multiply. 1 times 10 is 10. Add those together. That's 10. 1 times 10 is 10. Add those together. That's 10. 1 times 10 is 10. Add those together. Now we're at 7. Multiply 1 times 7. Add those together. It's 8. 1 times 8 is 8. Add those together. It's 2. Okay. We see that there is a remainder, and it's going to be 10x to the 4th plus 10x to the 3rd plus 10x squared plus 7x plus 8 would be what we get when we take this x minus 1 as a factor. But here's what we want to notice here. The sign of all of these are all positive. All positive. When they are all positive, this is an upper bound. Meaning there are no zeros larger than 1 because all of these are positive. All of those coefficients are positive. So we could test 2 and 3 and 4 or any number larger than 1, and it will never be a 0 for this graph because we just proved there's nothing larger than 1. 1 doesn't even work, actually. So we're not even 1 because we have a remainder. But this does prove upper bound. Anytime you do synthetic division, you have all positive numbers, there will not be a 0 larger than what you just tested. That is an upper bound test. Now let's check 0, and there's a lower bound test. All right, so we're going to do 0 into the same thing. 10, 0, 0, -3, 1, -6. Okay, we're going to drop that 10 down. All right, so 10 times 0 is 0. Add those together is 0. 0 times 0. Add those together is 0. 0 times 0. Add those together, it's -3. 0 times -3 is 0. Add those together, it's 1. 0, -6. Okay, this is not all positive, so we know that there is zeros that are larger than the number 0, right? But, and zeros are a special case. Zeros, when you're checking this, zeros count as positive or negative. We can count them either way we need to. So when we look at this, this is a positive, a negative, a positive, a negative, a positive, a negative. When you have alternating signs all the way across, and we can count 0 either way, so we'll do it the way we want to test it. Plus, minus, plus, minus, plus, minus. This is a lower bound. Lower bound because it alternates. And 0 can count either way if you're checking for alternating. 0 can count either way up here if we're doing positive. If we had 2 zeros in a row, that could still be counted as all positive. Okay, so we know all of the zeros for this graph are between here. There could be up to 5 real zeros. There could be no real zeros. But being that 5 is an odd number, we know that the ends, one end is going to go down and the other end is going to go up. So it has to have at least 1 0 because it's going to go from negative infinity to infinity because this is a positive and this is a odd number exponent. So we know whatever the graph does in here, it is going to cross and have a 0, at least 1. It could have 3, it could have 5, but it's going to have at least 1. So we can, at that point, graph it. So if I enter 10x to the 5th minus 3x squared plus x minus 6. Okay, that is the function that we started with there. 10x to the 5th minus 3x squared plus x minus 6. And I hit enter. Okay, let's zoom in. We see the graph is just crossing in one place there. And if we zoom in, the menu, window, zoom, I'm going to set my window settings. And I want to put the minimum x 0 and the maximum x at 1 because we know all the zeros are between x and 1. So I see this, it's almost at 1 where it crosses. It's way down on this end, way down on this end. So if we wanted to check the zeros, we know through our test, all the factors of -6 could be 1, 2, 3, and 6, right? Plus or minus for each one of those. 1, 2, 3, and 6. And all the possible for the coefficient of 10, we got 1, 2, 5, and 10, plus or minus. So if we were trying to check to see which of these, nothing over 1, because this would be 1, 2, 3, and 6 as possibles, and we know there's nothing larger than 1. Let's just do the fractions that are smaller than 1. So we can have plus or minus 1/2, plus or minus 1/5, and plus or minus 1/10. Well, looking at what we graphed, we can throw all of those out because you know it's almost 1. So it's not going to be any of those. It's not going to be any of the whole numbers. It's not going to be any of the where the 1 and 2 is the bottom. The next ones we can check is 1/5. These are all plus or minus. 2/5, 3/5, and 6/5. 6/5 is larger than 1. 3/5 is not close to 1. It's only about 0.6. So all of those can be thrown out. So let's look at the next ones. 3 over 1 is 3. 3 over that's 1.5. So 3/5 again. Oh, we just checked the fifths. I'm sorry. The tenths. I'm sorry. 1/10, 2/10, 3/10, 6/10. Let's go to sixes. I'm sorry. 6 over 1 is 6. 6 over 2 is 3. 6 over 6/10 would be the other possible one there. So we're looking at these, and they all seem to be numbers that don't really come into that. So what we see is we compare the x-intercept of the graph we saw on the calculator with the list of possible candidates for zeros, and we decide that f of x has no rational zeros, only irrational. We want to talk about complex numbers. Lesson 2.04 is going to have talking about complex numbers. And a complex number deals with I. I is a number in mathematics. I is equal to the square root of -1. Square root of -1. So we can use that mathematically because then we can square it. I squared. So if you square this, you just get -1, right? Because the square root of -1 times the square root of -1 would be -1. I to the third. So that would be negative square root of -1, because -1 is this. I is square root of -1. I squared is -1. So -1 out front would be a negative square root of -1. And then we'll deal with I to the fourth, which would be I squared times I squared, which would be -1 times -1, or +1. So when you deal with I, you always have one of these as your end result. If we go I to the fifth, that wraps around to where the same as I, because it'd be 1 times, so it'd be I to the fourth times I, it'd be 1 times this. All multiples go in a cycle of 4. I to the fifth, sixth, seventh, eighth, I to the ninth, 10th, 11th, 12th, I to the 13th, 14th, 15th, 16th. It's all going to wrap around and be one of these results for any power of I. So we've got to remember that. So a complex number is basically all real numbers and imaginary numbers. We're going to deal with imaginary numbers. Let me write, this is what it looks like. This is the way that is written as a complex number. And A and B are both real numbers. So for example, 2 plus 3i is how we write a complex number. 2 is the real number part of it. Okay, that's the real number. We actually have 2, and then 3i is an imaginary number. And we will deal with this in mathematics. We can use imaginary numbers to do mathematics. And you can actually graph imaginary numbers, but graphing those requires using a different graph than just our usual XY graph. And it will talk a little bit about that in the lesson, but I don't think it's going to actually show a graph. You can look up a graph of how to graph complex numbers, and it's kind of a three-dimensional type thing. It's pretty cool. But we can do operations with complex numbers. We'll do operations with them. So let's look at the different operations that we do with complex numbers. We can add, let's say 7 minus 3i is a complex number, and we can add that to 4 plus 5i. Adding complex numbers. And the way you do that is you have to add the real number, 7 plus 4, and then you add the imaginary numbers, -3 plus 5i. So what this ends up as being 11 plus 2i. But to run out of paper there. 11 plus 2i. You add the real part, you add the imaginary part. So -3i plus 5i, but I just put them in parentheses. 11 plus 2i. We can subtract them. Let me move over this way a little bit. So if we have 2 minus I, and we're subtracting 8 plus 3i, that gives us 2 minus 8 as the real portion, -i minus a 3i. -1i minus 3i. 2 minus 8 is -6. -i minus 3 more I is -4i. I don't want to get that confused. I'll put in parentheses. So we got -6 minus 4i when we take these and subtract them from each other. All right. There's an additive identity, and that's the terminology I use in there, where if you have a plus bi and you add to it -a minus bi, you're going to end up with 0 plus 0i, which is 0. That's mean additive identity. That means what does it take to zero it out? Negative a minus bi would be the opposite of that. When you add those together, it's going to zero. So they call that the additive identity, the additive inverse. The additive identity, the additive inverse would be 0. What it takes to zero it out. So some of the properties for real numbers are also valid for complex numbers, right? So the associative property of addition and multiplication, the commutative property of addition and multiplication, the distributive property of multiplication over addition. So from this, since these work like this, we know one of the properties that we talk about is x plus 1, x minus 1. We know if we multiply that together, that's just x squared minus 1. Knowing this property, that middle term disappears when you have a plus and a minus, that works when we talk about complex numbers, because that gives us opportunity to do something called the complex conjugate. And they'll cover this in the lesson. All this is in the lesson in more detail. I'm just giving you just a taste of it. So if you have z equals a plus bi as an imaginary number, then the conjugate of that, and the conjugate of that would be a minus bi. And here's how we use that. If we have a problem that we need to, let me put on some paper, that we are trying to do some math of this. 5 plus I divided by 2 minus 3i. And we're like, okay, how do we do that? We use the complex conjugate. We multiply by 1. And this is what our 1 is going to look like. 2 plus 3i over 2 plus 3i. That's just 1, right? It's like having 2 over 2. 2 divided by 2 is 1. 2 plus 3i divided by 2 plus 3i is 1. I'm multiplying this by 1. But the reason I do that is because we need to get this imaginary number out of the denominator and be able to rewrite an answer for this. And when I do this, I multiply. These are got to use the distributive property, right? So that's going to be 10, and then 5 times the second one plus 15i, and then distribute the i plus 2i, and I times there is plus 3i squared. All right, and then on the bottom, we've got 2 times 2 is 4. We know that the middle term goes away. This was that property we just looked at. When we know that we have an x plus 1 and x minus 1, we don't have a middle term. We just have the first terms and the last term. We know automatically to do that, this is going to be 4 minus 3i plus 3i. So this is going to be 4 minus 3i squared. I can put that in parentheses. Minus 3i squared. So simplify that. What is 3i squared? It's negative 9, right? Because 3 times 3 is 9. I times I is negative 1. So this is 4 minus negative 9, or 4 plus 9. Because the i's, remember our properties of i's, I times I squared is a negative 1. So this ends up a positive 9. So that simplifies. And now that we've got this, we need to simplify this as well. Because 3i squared is the same thing. Oops, work it over. 3i squared is the same thing as negative 3. Because this simplifies to negative 1 times 3. So we have 10 minus 3 is 7. And then we add those together, it'd be 17i. And then on the bottom, we simplified to 4 plus 9. Oh, which, let me go ahead and simplify that again. 4 plus 9 is just 13. So we can simplify that to make it a complex number. We divide out the real part. 7/13 is the real number. And the imaginary part is 17/13 I. 17/13 I. So we got 7/13 plus 17/13 I. That's what you get when you take 5 plus I and divide it by 2 minus 3I. Multiply by the conjugate, which is the conjugate, and then simplify from there. But be careful. I times I, I times I times I times I times I times I, right? It's going to change it from -1 to +1. So pay attention to what you have going on, what exponent is on your I, so you can simplify that correctly. That simplified to -3 right there. And that simplified to -9. All right, last thing I want to talk about, and like I say, your lesson goes into some better detail. When you have a quadratic equation, which we know what a quadratic looks like, ax squared plus bx plus c equals 0. You know, when we have it in that way, we can use the quadratic formula, right? The quadratic formula. And negative b plus or minus the square root of b squared minus 4ac over 2a. Well, this part right here determines everything. That's called the discriminant. The discriminant. B squared minus 4ac. This is the discriminant, and it will tell you a lot. When you put this b and the a and the c in there and you solve that, if this is greater than 0, right? If this is greater than 0, there are 2 real solutions. If this is equal to 0, then there is 1 real, it's a repeated, right? Repeated solution. Like the answer may be 2 and 2. It'll be the same answer twice. But before, when we talk about it, if it's less than 0, we always said there was no solutions. Because if it's less than 0, that means there's some negative number in here, right? And we'll just call it x, negative x. There's a negative number in there. Before, we always said there's no real solution because we hadn't got to complex numbers. This means there is a complex conjugate. Conjugate pair of solutions. So there's always solutions, but these are complex numbers solutions, because that's when you end up with the 4 and then plus or minus, and you end up with like the square root of -9 over 2 or whatever you end up when you did your quadratic. We always said, oh, well, that's a negative. There's no real solution. Well, now we know it's a complex conjugate. This is actually 4 plus or minus 3i, right? Because the 9 can come out and it just leaves -1 in there, which is I over 2. So this would be 2 plus or minus 3/2 I. In this case right here, because the 4 over 2, we pulled out the real part of the solution, 4 over 2, which is 2, and then plus or minus the 3/2 I is the complex conjugate portion. So there's always solutions, but these are imaginary solutions. So when you graph that, it would not cross the x-axis, but if you graphed it on a imaginary and a complex graph, you would have a way to graph those imaginary zeros that the quadratic has right there. So that's a lot of stuff I threw at you, and I kind of almost got lost in it myself in there because we're going deep. We're getting into good stuff. Synthetic division, wonderful thing. Conjugate numbers. When will this be posted? I will have it posted today, Anne Maria. I will have it posted today. I just gotta get it downloaded and uploaded and all that good stuff because it saves it for me, and then I got to reformat it. So I will look at that. I will get the recording done and upload it today, so you'll have that. But go through these lessons, read them carefully, practice it on paper. When you see that, write it down. Make sure you can work the problems that they're doing. It does have some of those check your answers in there, so you can make sure you're understanding. Go back and watch this video. I'll go back and double check my math because there's a lot of it in there that I was trying to do and not take up the whole hour and a half. So I may have got some things bumbled up a bit. And if I do, I will make sure I point that out in the video if I mess anything up. But I think I got everything correct on that. It's a good review for me as well. So, all right, I will let you guys go. If you got questions, then come to class next time and bring your questions. I'll be happy to answer them. Have a great day.
Let's get out of here. Word to your multiples. Math, baby.